Okay, welcome to Partial Differential Equations, Lecture 8. So this last time we had a look at second order systems. We derived the characteristic equations and we looked at the three different types. And what I'm going to do today is just give you two examples to start that basically is the way I solve actually all problems. I don't remember the derivation, I just do it repeatedly that I get fitted it, which is why I wanted you to actually go through the general one yourselves. So just to recap basically what we did last time is we started with a linear second order equation which basically looked like this. A, B, C, D, E, F, G were functions of x and y only, and we then said, or rather this theory actually comes from a general quasi-linear case, but we basically found that the characteristic equation you could write down in the following way, and the characteristic equation was basically the equation for a certain curve which, if you're given data on, you can use to construct the solution. It was basically came out of when we examined the Cauchy problem. And anyway, so here it is, dy dx is equals to that, which describes a curve. What it can also be written like is implicitly, if you say that phi of x and y is constant along a curve, the characteristic equation is as follows, and we stopped there, right? And then we went on and we said, what can we, if we're given an equation like this, what can we do to make it simpler? In other words, what can we do to write it in its canonical form? And what we said is, well, we can transform the variables, and we worked out the consequences of that. So we transformed to two new variables, and for now, this phi is not the same as that phi, but it sometimes will be. And we found that the linear equation transformed to a new linear equation with coefficients that were different, and the linear equation was now in new variables, 8 and xc, but the structure remained the same, okay? And in fact, we even proved by constructing this combination that the type of the equation is exactly equals to the type of equation that we got from the characteristic equation of the initial one multiplied by the Jacobian of the transformation. So provided your transformation is 1-to-1 and onto, and the Jacobian is non-zero, then the two types of the type of the equation is unchanged by a coordinate transformation. Okay? And we then went ahead and said, therefore, the type of the equation can actually be a feature of the equation at that specific position in any coordinate system. And we found that there were three possibilities. Either you have the hyperbolic case, in which case you have two real solutions to this. And we then argued that if you have the hyperbolic case, you can choose your new coordinates to be exactly the characteristics and satisfy that equation, which basically then puts these coefficients to zero. Okay. And then you would choose your other coordinate to be the other one, put that coefficient to zero, and then you would be able, and you could also show that b is not equals to zero, and then your form, or the final form for a well-chosen transformation looked like that. So it greatly enabled us to simplify differential equations into that form. Similarly, we said that if for the elliptic case, you have the case where this thing is imaginary, over there in the square root, and therefore you don't have real characteristics. But we said, and this I will prove if I have enough time at the end of the course, or sorry, end of the lecture, sorry, that you could still choose psi and phi so that A is equals to C and B is equals to 0, and you could reduce your elliptic case to this thing. Okay, so there are two cases. In the final case was the parabolic case, where you only had one characteristic, and you immediately choose your coordinate to be the characteristic coordinate, which permits you to put A phi to 0. You can't put A psi to 0, but you can set B to 0. So you're then left with the canonical form, which looks like that. Okay, so that's what we did during the last lecture. I just wanted to put it up here to sort of set the stage for what's coming. What I'm going to do now is I'm going to get a differential equation and show you the steps I go through, which basically mirrors this, but sometimes if you see an example, it's just clearer. And it's sort of what I recommend you do when you solve the problems, but obviously I said I don't have a recipe, so anything you find that actually gets the right answer, and that you, once you've got the answer, differentiate it back and could prove to me that it is the right answer, is absolutely fine with me. Okay, so the equation I'm going to look at for first principles is something like this, right? So the first thing to check is the type of the equation, and the way I check the type is I take the highest derivative. If it is linear in the highest derivative, or even quasi-linear in the highest derivative, I basically group the coefficients of the highest derivative together. If you have u and ux in there, it's quasi-linear, and you can still work out the characteristic equation. You cannot always solve it, because it will be implicit. If the coefficients depend only on the independent variables, namely x and y, then I have them, and I label them according to the ABCD that we've had in the previous, that we've been working on in the theory. So for this particular case, we have A, which is the coefficient of uxx is equals to y, B, the coefficient of 2b, is the coefficient of uxy, so we have b is equals to x plus y over 2, and c is the coefficient of uyy. Okay, so it's just to get it in the same type of structure that we've been looking at. Then the next step is all those others were 0, because they're not there. And then I immediately write down the characteristic equation so that I can identify the type of my equation, and I can get a feeling for where I'm going. Okay, so the characteristic equation is that. I've just taken the denominator out over here and put it in there so that it looks nicer. I substitute in A and B and C, and I get this equation. Okay, which I can actually simplify, or because this is a square, right? And I don't have to worry about the plus minus of the square root because it's already out there. So I basically, this characteristic equation then becomes two equations. If I use the plus, it's simply y dy dx is equals to x, and the minus branch is y dy dx is equals to y. Okay, so that these two options are just this thing written out, and these are reasonably simple differential equations which I can integrate. Okay, so the first one, what I would do is I have y dy minus x dx, and I want to integrate that. I can just integrate each partial independently, and I get that. Okay, so you have y dy minus x dx, and you integrate that, and you have y squared minus x squared, where I've multiplied through by a half, is equals to some constant which I call c. And if I to integrate the second one, I just divide through by y, and then you have dy is equals to dx plus a constant. So what I have is y minus x is equals to the second constant. So there I have explicitly solved my characteristic equations, and I can immediately see, because they're real, in other words, because this thing was not negative, the thing in the square root was not negative, that I'm dealing with a hyperbolic system. And I'm going to now transform onto these new coordinates, and simply, for this specific case, and simply show you that I actually get out the form that I derived. So I'm actually going to go through exactly the steps that I did for the derivation, but it's just easier to see sometimes if you're actually working with concrete functions. Okay, so here C and eta, we're going to, our integration constants when I integrate this, the characteristic equations. But what I do to find the new variables is I elevate them basically to new variables. So the characteristic constants, basically, if you think about a line plus a constant, right, it gives you a family of lines like that on the axes. And so the constants basically label which line you have. So I'm basically changing to the new variables where the constants are now the new variables. So, okay, so these constants become the new variables, and the variables themselves are constant along the characteristics. And now let's change the variables to be able to do that. Okay. So to change the variables, you need to work out what the derivatives are of u with respect to x are in terms of the new variables. So here we want du dx. So you just use your chain rule. Du dx is just du dx times dx dx. So there's where the minus 2x comes in from the front over there. Plus du d eta times d eta dx, which is why there's a minus over there. And you want the other derivative of du dy, so du dy is just du dx times dx dy, and dx dy is just from this expression 2y, and then plus du d eta times d eta dy, which is just 1. Okay, are you clear on where this comes from? The partial, this expression. You can get that. Okay, so you have a function of two variables, x and y. Okay, you want to work out the derivative of that function with respect to x, but you've transformed it to new variables. Okay, so to transform it to new variables, you say that. So you basically have u of x and y, and you want new and you know that you want u of c. You want u of x. Okay, you know u of x and y is equals to u of c of x and y and eta of x and y. Right? So to work out ux, you have du dx is equals to, okay, to take a derivative there, it's du d eta times the eta dx. So you have the eta dx plus du d, this is c, this is eta, du d eta plus the eta dx, times the eta dx. Okay, so du dx is equals to this in the new variables. And then you simply, and that's what I wrote up there. And for this particular example, you have the dx is just equals to minus 2x. That's where this one comes from. And the du d eta is just equals to minus x. That's where the minus comes from. So this thing you should know. Okay, so now you know where it's coming from. Okay, cool. And then you do it again when you go for the second, the uxx. Okay, so to get the uxx, you basically do the same thing but to ux. Okay, so you first say, I want to take ddx of the top thing, so I first get a term that, I want to take ddxc of this thing. So the 2x, you wait for a bit, so then you get minus 2, and then you take ddxc of uxc, so you get uxc, and then you have this thing that's multiplying it, times another one. So you have 4x squared. Okay? And then minus, sorry, let's just wait. Okay, minus ddx of that thing, because the things that I'll just have x's in you can differentiate directly. So there's where the minus 2c comes from. And then you want ddx of minus u eta. So then you basically have minus 2x times ddxc of u eta minus 2x times dd, eta of u eta. Okay. And then the second term, and then you have this one coming in as well. Sorry, you have ddx, wait, we're going to start again. So you want ddx of this thing. Okay. So you have first ddxc of this thing, okay, times by minus 2x. So ddxc of that thing is just ucc, minus 2x times minus 2x, so that's where the 4x squared comes from. And ddxc, and then you have ddxc of this thing times minus 2x, which is where that thing comes from. Then you have just ddx of that thing, which is where the minus 2 comes from. Okay, plus dd eta of this thing times d eta dy, which is equals to 1. So you basically have dd eta of this thing comes, d eta dx, which is minus 1. So you have minus dd eta of that thing, which gives you those two terms. Okay, so if you get confused, what you need to do is you take ux. So you want uxx, okay? So that's equals to u of x times x, right? And what you do is you substitute in what we have for u of x. So you have 2x minus uc minus u eta, okay, and you want the derivative of x of this thing. Okay, so I've basically taken u of x, which is going to be easier if I write it here. So you have u of x is equals to minus 2x u of c minus u of eta. Okay, you now want uxx, so you want to take the x derivative of this thing. Okay, remember the x derivative, you can apply the product rule, so you can immediately take the derivative with x that just remains here. Okay, so that's equals to minus 2 uc. Okay, but these things, to take their derivatives, you actually have to apply the product rule again. So you have plus dd eta or ddxc of minus 2x u of c minus u eta times minus 2x. Okay, because you have to work out dxc dx. Okay, plus dd eta of minus 2x u eta minus u, uc u eta times d eta dx, which is minus 1. Okay, and this is then equals to minus 2 uc plus, okay, so you have minus 2x, so that's 4x squared u, this c hits only that one, so it's c plus 2x times u eta c. And then you still have to add this thing back, so you have plus minus 2x u of c eta. There's another minus at the back, so it's actually plus, and the minus goes in here, and so you have plus u eta. Okay. Go through it, do it yourself, check it, make sure you get fit to be able to do it, because you're going to be doing this a lot. This is exactly what I did yesterday as well in class, which is why I wanted you to go through it then. Okay, so that's uxx, uyy, you compute in exactly the same way, repeatedly putting that operator on top of each other. And what you do now, you also have uxy. You basically only have to compute the ones that appear in the equation, the original equation, but here all of them appear, so there they are. And so you have uxy, which you also do in exactly the same way, and there you've got that. Okay, so now the next step is you take these derivatives that you've transformed into the new coordinates and you put it back into the original equation. Okay, so you substitute it into the original equation and you simplify, and the way you simplify it is you gather up the coefficients of the second derivatives. Just like I did when I did the proof, I wrote down the second derivative and then everything in front of it, and that's what you get. Okay, so it simplifies beautifully. In fact, you lose your second derivatives in cc and eta, just as to be expected because you're dealing with a hyperbolic equation. Okay, so that's where you have very strong checks when you do partial differential equations. Know the theory, but work it out independently and make sure that the things cancel as you expected it for a hyperbolic equation. Okay, and the last step is this differential equation has to be written in the new variables. So you have to go about and replace x minus y in these cases with functions of x, c, and eta. And fortunately, in this particular case, it's easy because x minus y is just minus eta. So you then put that in, and you get that differential equation. So you can see this thing is much simpler than that one up there. Okay, and in fact, this thing you can now solve. Can you see how you would do it? Okay, if you want to solve them, the first thing you have to do is factor things. And the second thing you want to do is see if there are derivatives of something, if one term is the derivative of another one. So you can actually write this thing, if you divide by eta, which you're allowed to do, you can rewrite this thing as dd eta times eta uc. Okay. So those tricks are things you're going to have to practice. So go through this example carefully again, go through the problem sets again. But they're usually not complicated. Usually the one term to simplify it is the derivative of another one. And you get that. I won't ask more complicated things than that. There are a few other tricks, but that's not the main focus of the course. Okay, so always factor out, take out all the common factors and then see if you can write the term more compactly. And the moment you've written it like this, you can now integrate it, okay? Because that basically means that eta UXC does not depend on eta, so you can write n times UXC is equals to a function of xc, just like we did with the wave equation. In fact, that's the power of hyperbolic systems. You're basically reducing them almost always to something that has a wave equation plus lower order terms. That is what the derivation says. And as a result, you usually can write down the answer like that. Okay, so we've integrated once. Eta times UXC is equals to f of xc. You can integrate it again by simply writing u of eta is equals to that. And when you integrate it, you get this, right? So remember, when you integrate it, you're integrating only with respect to xc. So you basically have this, the integral with respect to xc of big F over eta, which I've just called another function, because the function is arbitrary. You can't, it doesn't matter if you relabel it, plus an arbitrary constant g of eta. And so the general solution you get, you can write, usually whenever I do it, I put it back into the original variables. And the way I put it back, is just to replace xc with its definition and eta with its definition over here and over there. And so you can actually write down the full general solution to that problem, and these f's and g's are then fixed by your initial data that you've set on. So it's kind of powerful looking for these coordinate transform, the characteristic coordinates, and it allows you to actually gain a lot of insight. A lot of physics and stuff has been done by looking at these general solutions and studying their properties. And it's nice because there are only 3 basic types that you start looking for. Okay, so just basic, when you get something like this, look at the differential equation, identify the things that go into that characteristic equation, determine the type of your equation, and then if it's hyperbolic, change the variables onto the new coordinates. The transform the differential equation. That's where the work comes in, right? It's not hard work, it's just systematic work, and don't make mistakes. Once you've got it, make sure that the coefficients of eta and CT in the new variables vanish, because you are dealing with a hyperbolic equation, and then try and integrate it. Okay. So now what I wanted to start discussing is another differential equation, and we're going to do basically the same. The nice thing about this course is if you remember, once you've got it in what to do, it's the same type of thing for almost all second order differential equations. So it's a nice set of techniques. And in fact, well, I'll start showing you with elliptic equations. I almost cheat, and I can actually do the same method for the elliptic equations as well, which is not something that was actually in Fritz John as easily. I've just always done it like that, and I've always gotten the right answer. So I'll show you the two methods. Okay, so the next example is something they call the Tricomi equation, and that thing comes from people that studied shock waves. So it's one of the simplest examples of where an equation changes type based on where in the actual XY plane you are. And it's sort of the simplest example of when your plane goes through the characteristics and it makes the sound make boom and sends the shock wave out, of how to deal with that. So it's a very interesting equation. As I said, it's used to study transonic flow. That's where you go through the sound barrier. And it's a very simple equation. Okay, so here you have uyy minus y times uxx, like almost a wave equation, but not quite. And so the first step, as we always do, is to put it in the standard or the canonical form. To do that, you basically identify your A, sort of all the things that we went in when we studied the quasi-linear equation. So you have A is equals to minus Y, in other words, the coefficient of uxx. C is equals to 1, which is the coefficient of Y. And then all the other things that we were used are set to 0. And so when you write it in that form, the thing that goes into the square root and determines the type is simply AC minus B squared, which is equals to minus Y. So this equation, you can now see if Y is positive, this thing is negative. If it's 0, it's 0. And if Y is negative, this thing is positive. So depending on the sign of Y, in other words, whether you're in the upper half plane or the lower half plane or on the axes, you have different types of equations. And so let's just write them down. So if Y is equals to 0, you're parabolic, so you have one characteristic solution. If Y is less than 0, you're elliptic. So you have no real characteristics. If Y is greater than 0, then you're hyperbolic. Okay. And so your characteristic equation, next step, solve the characteristic equation. It is simply this thing, and I actually used one of the earlier forms there. And so you can say that you are solving dx plus minus the square root of y dy is equals to 0. And let's first look at the hyperbolic case. So where y is greater than 0. And I'm going to defer the elliptic case until I've discussed it more generally. So y is greater than 0. This is the characteristic equation, and you can solve it by integrating it. And you simply get the integrator of dx is x, plus minus the integral of the square root of y dy is simply 2 over 3y to the 3 over 2 is equals to a constant. Okay, so we've integrated it, and what we get, and I just wanted to show you this picture. If you plot this x is equals to plus minus 2 over 3, you have two branches, y to the 3 over 2, you get these curves like this. So basically our new coordinates we're going to choose to be, I've just multiplied through by 3x minus y, 2y to 3 over 2, and the other one, eta is just going to be the plus branch. Okay, and those new coordinates are basically plotted over here. So in some sense, the new coordinates are the implicit forms of the characteristic lines. So here you have C has a positive slope, so C branch is the ones that like lean towards the door, and eta arches a left. Okay, so you have these ones over there. So our two new coordinates basically sort of describe the characteristic lines, and you can see that when y is positive, they basically form new coordinates, right? They don't cross at 90 degrees, but they do form new coordinates. What happens, and this is why the thing became interesting, is when you start going closer and closer to 0, the type of your equation changes, and the characteristics basically go from 2 to characteristics that are tangent to each other, and so they disappear. Okay, so the cusps at 0 is what happens when your hyperbolic equation changes to a parabolic one. Okay, and as I said, it results in dramatically different techniques to solve them and results actually. But it's not a jump. There's a smooth transition from hyperbolic to parabolic to elliptic, just as there's a shock wave and then a smooth transition when you cross the sound barrier. Okay, so now that's sort of the context of where this problem comes from. from purposes of this course, you are going to have to analyze it. So next thing we do is we transform, once again, these equations into the new variables. Okay. And the new variables basically work just for the hyperbolic case. So let's now do it. Okay. You once again work out ux. So du dx is equals to du dx times dx dx. So that's 3. Okay. Plus du d eta times d eta dx. So the 3 comes from over there. Okay. Du dy is slightly harder because y is more, there's a function there. So you have du dy is du dx times dx dy. So dx dy is equals to minus 2 times the derivative of this thing. So that's 3 over 2 times y to a half. So that's where that one comes from. And then you have du d eta, plus du d eta times d eta dy, and d eta dy is just the derivative of that thing. Okay, so that's where that expression comes from. It's exactly the same chain product rule and then chain rule that I applied up there. Okay, the next derivative you do in the same way, and what you get is that uxx is equal to 9 times uxc. Basically, all these variables appear, and duyy, you again do exactly the same way, and you get something like this. Okay, and now what do you expect if you put these two back into this equation? Is that because we're looking at the hyperbolic case where we have two characteristics, you should only be left with u8xc. Okay, so there we go. We've substituted this thing back into the original equation. Here we have uxx. Here we have you have uyy, and then you have minus y uxx over there. And if you simplify it, that's what you get. Okay. So with these things, there's this very complicated step where you work out the second order derivatives, but you know where you're going. So, but go through the algebra carefully, and then you actually get that the equation for the hyperbolic case is minus 36 times uc eta minus this thing, which is a lower order term. Okay, so it very clearly becomes a hyperbolic equation. Right. The elliptic case, remember I said in the first slide, the elliptic case, it's always possible to pick A equals to choose A is equals to C, and to set B is equals to 0. So I'm going to give you what's known about the elliptic case, and I'm going to give you what I do, which I find easier. Because what's known about the elliptic case, if you look at Fritz John, where this work is basically coming from, it's chapter 2, they give you a certain result, but it's actually quite hard to solve the equations of that result. What I practically do is simply to solve the characteristic equations, even though they are complex, and then choose them really imaginary part, and those are the right coordinates that seem to work. Okay, so let's have a look at the elliptic case. Before I go on, any questions about this example? Okay. It becomes clearer when you go through it, but you must go through it. Right. Keep the pink part and try and do the rest yourself, just to get fit. And if you get stuck, come and ask me. Okay. So I just simplified it to get the normal form, or the canonical form over there. Right, elliptic equations. Okay, so elliptic equations, what I'm going to do is first discuss what I do and then give you the results that Fritz John gives, and then give you an example possibly in the next course, in the next lecture, about how to apply it. So with elliptic equations, you have this thing that goes into the square root sign, minus this thing that goes into the square root sign is negative. So I'm going to call W, it's basically the positive part, or the ordinand, or the number on the thing. Okay, so you have omega squared is equals to AC minus B squared. There's your characteristic equation. So if we now write the characteristic equation out, record with where this thing is, we know this thing is positive, we get that you have dy dx is equals to b plus minus I over a. Okay, so you have a complex equation. Have you done complex analysis? Okay. Complex equation. The solutions are complex. What's also complex is that if we've written this thing in terms of the implicit form, okay, remember these two are the same. Okay, these solutions are also complex, and if you ever try and solve this other one with different variables, you also have complex solutions. Okay. What I do is I don't let it worry me. In practice, I simply define my new variables to be the real and the imaginary. I work out the solution, the complex solution, then I take the real and the imaginary part to be my new variables. And when I do that, then I actually, in all the cases that I have tried, I've gotten the correct variables. Okay. Okay. And the main insight is they're complex, but they're complex conjugates of each other. So what I do in practice is basically I just choose the real and imaginary part of these functions as the new variables. What the result in Fritz John is what I'm going to give you now, and I'm going to prove it. And then they should be, I suspect they are the same. I have not proven them the same. So if anybody comes up with a proof that the two methods are actually the same, you can get a bonus point for some of your tutorials. So that's what I do in practice. Fritz John proves that he makes the following statement. He says, if you can find solutions to these equations, or such that phi of x is equals to b times psi of x plus c times psi of y over w, and phi of y is equals to a times psi of x plus b times psi of y over w. If you can find that, he doesn't tell you how, but the theorem goes, if you can find those two, then you can actually prove that statement that I made earlier about you can set both a and c equal to each other and b to 0. That's what he now proves. Okay, so that's true. What he does then is he substitutes these two into a. Okay, so that's what he's done. There we go. Right. And then you can basically, you just multiply it out and you get that. Okay, and when you do that, you can notice that here above the line you have things that look similar to w squared. In fact, if you factor a out over here, you basically have w squared over w squared. So you're left with a times psi of x plus c. If you factor c out here, you have w over w psi of y plus 2b psi x psi y. So what he proves is that provided you can find any solution that obeys, any pair of solutions that obeys this, you can always set both a and c equals to each other, and if you substitute it into the expression for b, which is that, you can show also that b vanishes. So this is a theorem I stated in the last lecture. So there I'm substituting it. I've simply taken this definition of phi of x and put it in there. I've taken 5y from here and put it in there. And similarly here, 5x and 5y have been substituted over there and there. And if you multiply that thing out, you can see that the terms cancel. And the way you can see that quickly is simply look at the coefficient of AB, right? So you have an AB there, which is psi x squared over w. You have an AB over there, which is a minus psi x squared over w. And all of them cancel out, and you're left with 0. Okay, so Fritz John says, make this assumption, which you can always, if you find that for a given psi, if you put phi of x equals to that, then you can always find the coordinate transformation. But it doesn't tell you how to find the first one. Okay, but all he says is that this thing, which you can always solve, in principle, though in practice it's hard, is enough to prove the normal form. When I do it in practice, I basically choose the real and imaginary parts of my characteristic solution to find the functions. So that's the little part that I add. Okay, so let's just look at it. The first example is the Laplace equation, which is the thing we study, and we'll look at several ways of solving it. So it's the example of the normal form without the lower order terms. The second one, so that's already in canonical form, and you just check it. So you have AC minus B squared is equals to 1. Okay. The second one I'm going to do now, because I still have time, is that Trichome equation, but with a minus in front, just to show you how that actually works, and to show you how I actually go getting the new variables that puts it in this form without having to guess. Okay, so let's go back. So this is I've just flipped the sign so I can assume y is negative. So that's exactly the Tricomi equation. We know it's an elliptic equation because we have I've lost my cursor. We've got a is equals to 1 and c is equals to y. So we basically have this AC minus B squared is equals to y, which is greater than 0 by assumption, and it's elliptic. And the characteristic equations then become dy dx is equals to plus minus I of y. Okay, so what I do now is I simply solve the characteristic equation in the complex plane, which you can do, and what you then get is that it is equals to plus minus 2i the square root of y plus x is equals to c. Okay, so to get from there to there, I simply divide it by the square root of y, and I put dx on that side, and then I integrated them. Okay, so that's our solution. And here I'm going to assume C is a complex number. Okay. So I'm going to choose new coordinates to be the real and imaginary part of C. Okay, so here I put C is equals to the complex number. So my new coordinate is x and 2 eta. Okay, sorry, 2 the square root of y. Now the important thing here, it has to be exactly the real and imaginary part. Simply putting eta equals to square root of y would create a mess. Okay, so there are now my new variables. And I can now go and I can transform that equation using these new variables that I got by strictly choosing the real and imaginary parts of my complex solution to the characteristic equation. And the method of transformation is the same by the stage ux, c is just equals to x, so ux is uxc, uxx is uxcc, it gets more complicated, uy is just because du d eta times d eta dy, so that's a half times 1 over the square root of y times 2. So it's 1 over y. The second derivative is just d dy of this thing. So that is simply 1 over the square root of y times d eta of this thing. So that's the first term. So you 1 over square root of y times 1 over square root of y u eta eta minus d dy of that thing. So that is minus 1 over 2 y to the minus 3 over 2 times u eta. Okay. So those are our new derivatives. And then you substitute that back into the original equation, and you can show that then it becomes the normal form you expect. Okay. So I don't view the elliptic equations as any more different than the hyperbolic ones. I just work in the complex plane. And then I choose the real and imaginary part for the new coordinates, and I'm done. Okay. I don't know why Fritz John didn't put that step in, but it's practical. I've used it. I've never failed. And anyway, it doesn't matter because it's a good guess. So the moment you've made the guess and you confirm that you get the right form, the standard form, then you're fine. Okay. So that's it. So here is the normal form of the elliptic equation. It's basically the one you expect plus a linear term. And the final step is you've got to always replace in the final equation of your normal form everything of your original variables in terms of your new variables. So you have to replace the square root of y, which in this case is simply eta over 2. Okay, so 2 times the square root of y is 1 over 2 times, a half times 1 over the square root of y is just 1 over eta. And that's your normal form. Okay. And yeah, this one I don't know how to solve exactly analytically, and I'll also not ask you to do things that aren't obvious or easy to do. Usually if I ask you to find the answer, it's because there is one. That's the luxury of being a student. When you start solving real problem or sort of problems that don't have a previous solution, then it's harder because you don't know if you're actually looking for a real solution. In fact, it's become so hard that most people don't, right? The ideas of looking for analytic solutions, most people do numerics, which is a reason to learn Python. So they basically solve the thing numerically. And that has feedback both ways. Being able to solve it analytically is nice. You have a tremendous amount of control of the solution. You have a tremendous amount of being able to understand the solution. Because if you do a numerical thing, all you do is you start with initial conditions and you find that one solution. Whereas if you actually understand the structure, you've understood it for the whole array of initial conditions. So there's a lot of benefit for finding the solutions. People are no longer fit in doing so. So it was actually interesting when I looked at solving certain problems in relativity analytically. People first laughed at me. And there's some I still have not solved that I think are solvable. But I started looking at the literature, and you sort of look at the modern textbooks for these things. And then eventually I stumbled across Cambridge's TREPOs. So Cambridge University had these famous mathematical TREPOs. In fact, they still have. It's like their entrance exam for their PhD or their undergraduate. And I looked at their exams from the just before the First World War, like 1902 or 1904. And I was like, wow, if somebody gave me this exam, I'd have a problem. They were very, very sophisticated in their methods of solving. And there are actually a lot more solutions and a lot more techniques than any university here or overseas is currently teaching. Because people have basically viewed the problem as too hard and simply go to the numerics. So what I'm saying is there are places where people have collected answers that are worthwhile examining if ever you have a problem. The one place is Cambridge's archive of problems. The other place is Baderman's integrals. You know, the dead guy that Did I tell you the story? Yeah. The guy that once he died, people went into his desk drawers and took out all his integrals, which he just stashed because he just worked them out because he wanted them, and then wrote 2 books about it. There's a tremendous wealth of integrals sitting over there. And it's worthwhile at least checking for them before you actually try and solve it numerically. And basically applying the things of this course. A lot of the stuff in this course actually is not always taught anymore, which is sad. But it puts you in good stead for solving problems generally. So that's it for now. Questions? I'll stop this recording thing and then take